So today, I hope you're all doing well. So now we're gonna look at the topic called the atomic combination for grade 11s. So without any further ado, let us go through the session. Now, number one, we will be looking at what we call the chemical bond. Now, when we talk about the chemical bond, what are we actually talking about? Now, when two atoms or two ions are held together in a molecule, we say we have a chemical bond. Now, for two atoms or two ions to be held together in a molecule, it's because of the sharing of electrons between those two atoms. For an example, say that we have ion or atom A, we have ion or atom B, and then now these two atoms, we have electrons that are being shared between them. Now, this compound, now it forms what you call a compound, or it forms what you call a molecule. Now, this compound or a molecule, since when we have the atoms that are being shared between them, now this will form what we call a chemical bond. Bond is a combination of two guys, and these two guys are bonding together because they are sharing electrons between them. And now we have what we call a chemical bond. They are shaking hands, right? They are connected to one another by those two electrons or those three electrons or whatever number of electrons that are found between them. Now, number two, we'll be looking at what we call the Lewis diagrams and the bonds. When we talk about the Lewis diagrams, we are actually talking about a presentation on how we form the chemical bond. Now, Lewis diagram, it is there to show us how does a chemical bond gets to be formed between the two atoms. Recall that you're going to have your atoms that are being separated and you would want to bond them or you would want to combine them. Now, when you combine your atoms, you should be able to do so by making use of your Lewis diagrams. And there are certain rules that are signed on how to draw a Lewis diagrams, and we will look at those rules and how to draw a Lewis diagram. Now, in this case, we have below, I will show you just now, we have a table for elements that are found in period number 2 from the periodic table. And this table will show or will guide us on how to go about for Lewis diagrams. So when you draw your Lewis diagram, you need what we call the valence electrons. And I will explain that to you. What does the valence electrons mean? Now, this is the table that I was talking about. We have elements that are found in period 2. If you still do remember, let me refresh your brain. What does period 2 looks like? So this will be period 1. This will be period 2, 3, 4. So, and 5 going downwards. Now, recall that from the periodic table, when you move like these rows, you are moving in a form of a period. So these are all periods, period 1, 2, 3, 4, and going downwards. Now, period 2, it composed of these elements. We have the lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, as well as neon. These are all elements that are found in period 2 of our periodic table, right? So what's special about those elements? It's not only about those elements, but we are just looking only, for now, we are only focusing in one period. Now, like I said, first element will be lithium. It is found in which group? Let's go back to the periodic table. So these are group numbers 1, 2, 3, all the way up to 18. And we can see that these numbers are also presented in Roman figures, but except starting from 3 all the way to 12. Here we don't have Roman figures. We call these elements the transition metals. So we're not gonna focus on them like that. So meaning 1, 2, and then we have 3, 4, 5, 6, 7, 8. That's how also we can look at our group numbers. So group number for lithium is 1. Where how many valence electrons do we have? Yeah. So now what is valence electrons? Valence electrons, we say those are the outermost electrons. Valence electrons are the electrons that an atom needs to donate, or you can say are the electrons that an atom needs to accept. The atoms that donate are called the metals, and the atoms that accept the electrons are called the non-metals. So when a metal donates an electron, it becomes stable. Or when a non-metal accepts an electron, it becomes stable. Okay? Now, when you talk about the valence electrons for group 8 elements, which we call them the noble gases, here, the valence electrons, there are 8, okay? But in this case, we say that the noble gases are inert. What does inert mean? Meaning they are unable to combine with other atoms. We say they are stable elements. They are stable by itself, okay? They cannot react or combine with other atoms. Except group 8 elements, look at this periodic table. All of these elements, they are unstable, okay? So when all of these elements combine or react with other elements, they will now be stable. How will they be stable? If they are metals, they will donate electrons for them to reach stability. If they are non-metals, they will accept electrons for them to reach their stability so that they can be like the noble gases. Right? So that's what we mean by valence electrons, okay? The outer number of electrons that will be donated, will be accepted depending depending whether the atom is a metal or non-metal. So for group 1 we have 1, group 2 we have 2 valence electrons, and group 13, or you can write it in Roman figure, which is group 3, we have 3 valence electrons. And then for carbon, which is found in group 14, or you can say it is found in group 4, by Roman figure, we have 4 valence electrons. So you can see that the group number corresponds with number of valence electrons. If it is in group 1, there's 1. So you go back to your periodic table, we have hydrogen, we have lithium, sodium, potassium, and so forth. These atoms, they are in group 1, meaning they have 1 valence electron. And then the group 2 elements, beryllium, magnesium, going downwards, these atoms or these elements are found in group 2, meaning they have 2 valence electrons. Do you get it? Lastly, and moving forward, we have group 3. Group 3, we have boron, aluminium moving downwards. This is a group number. It is in group 3, or you can say it is in group 13. So how many valence electrons do these elements have? They have 3 number of valence electrons. Okay, so that's how it usually works. Now, going back to this table, we have what you call the spectroscopic notation, which is called SP notation. Okay, it's what we did in grade 10. We must be familiar with this. Now, the SP notation, it represents the number of orbitals or orbits, right? We have S orbital, we have P orbital, and so forth. So in this case, I'm not gonna dwell too much on this because we have already done this in grade 10, just so that you see that these are the SP notations for these elements. So when they write He over here, it's indication of helium. This is the SP for helium. Yeah. And then now let's go to the Lewis diagram. The Lewis diagram, because our focus here is for Lewis diagram. Now for Lewis diagram, like I said, you look at the element, you look at its group number, then you conclude the valence electrons for that element. And then you draw your symbol for your element, which is Li. So what does this dot mean? This dot, it simply means the valence electron. Okay, so meaning around the lithium, we can see we have only one dot. We can do it in a form of dots, or you can do it in a form of cross. So this dot or this cross, it is only one surrounding the lithium. Why? Because this dot or cross, it indicates the valence electron. Okay, so lithium has only one valence electron, then we have one dot surrounding lithium. Now, beryllium, you check its group number, you see, oh, Be, which is beryllium, it is in group 2. Now, what are the valence electrons for beryllium? Meaning it's going to be 2 because it is in group 2. Therefore, how many dots or how many crosses will surround Be symbol? We're going to have 2 because we have 2 valence electrons. Like I said, you can do it in dots or you can do it in crosses. Okay. Same applies to boron. We have 3. You can see that we have 1, 2, 3. Same applies to carbon. We have 4. We have 1, 2, 3, 4 valence electrons. Nitrogen, we have 5. We have 5 valence electrons. Oxygen, group 6. The valence electrons, there are 6. We have 6. And then fluorine, we have 7 valence electrons. We have 7 when you count them. And neon is in group 8. It has 8 number of electrons. Now, there is something that I also want to talk about while we are here. And that it is called an octet rule. Okay. There are atoms that supposed to obey an octet rule for them to be stable. Like I said, metals will donate the electrons and the non-metals will accept the electrons. So when metal donates electron or electrons, it becomes stable. And when it becomes stable, it obeys an octet rule. When a non-metal accepts the electron or electrons, it becomes stable. And when it becomes stable, we say it has obeyed the octet rule. So neon doesn't obey octet rule, meaning group 8 elements, because so what we mean by octet rule, the outer energy level supposed to be surrounded by 8 number of electrons. So if the outer energy level it is surrounded by 8 number of electrons, we say that the atom has obeyed an octet rule. But there are atoms that do not, like for example, hydrogen, even what is this thing? Even lithium. Lithium cannot obey an octet rule because its outer energy level, um, it's gonna be after it donates, it's gonna be 2. It's gonna be like helium. Understand? Let me go back here. So lithium, it has 3 electrons, so it will donate only 1 electron. It will left with 2 electrons. Now it will be like helium. So atoms like this with lower energy levels do not obey an octet rule. Even the hydrogen atom. Recall that hydrogen atom, it acts as a metal, can behave as a metal and non-metal. Because hydrogen, it is a non-metal, but it is found in group 1. Hydrogen is a non-metal, meaning it can accept the electron. Hydrogen, it is in group 1, meaning it behaves as a metal, it can donate the electron. When it donates the electron, it becomes what you call a proton. Okay, but when it accepts the electron, it becomes what you call the hydrogen gas in a molecule. Okay, so that's why we say hydrogen can behave as either metal or non-metal. So even hydrogen, it cannot obey an octet rule because its outer energy level, it can take a maximum of 2 electrons. Okay, it can take even the beryllium. Beryllium, it is in group 2, right? It will donate 2 electrons and it will left with 2 electrons. Those are maximum number of electrons that are found in the outer energy level. Do you understand me? Then boron, it will accept because it's an by the way, it's a metalloid, it's a semi-metal. Okay. Um, I want us to come here to this one is a little bit complicated. Let's come to carbon. Carbon, it is in group 4. we need 4 electrons. It's a non-metal, it accepts. So carbon will accept 4 electrons. So when it accepts 4 electrons, it's going to be 6 plus 4, that will be 10. And then now carbon, it is the one that can obey an octet rule because the outer energy level will carry a maximum of 8 electrons. Okay, hope that was clear. Now, I want us to look at these are the things that you should familiarize yourselves with. Yeah, you will go through this. Basically, it's most of things that you understand. Like I said, noble gases have full valence shell. Atoms of other elements bond try to fill their outer valence shell is similar. So I have already explained some of this, okay? And then there are 3 forces that act between atoms. We have attractive force, repulsive force, and repulsion. So a repulsive force, okay, by the way, this is also repulsive force, it's the same thing. So when you talk about the attraction, we know that atom has 3 particles. Atom has electrons, atom has protons, atom has neutrons. Those are 3 particles that are found within the atom. And then the protons are positively charged, the electrons are negatively charged. So the attraction between a proton and electron, that's a force between a proton and electron, that will be attraction because they have opposite charges. But a force between electron and electron, it's going to be repulsion. Or a force between a proton and a proton, it's going to be also a repulsion. We will see this more especially when we do chemical energy, the bond energies, when we do those graphs. This is where this part will make sense. Now, again, this part again, the energy of a system of 2 atoms is at a minimum when the attractive and repulsive force are balanced. Again, we'll do this when we go to the energies. Now, we are on Lewis diagram, and then, like I said, I've already mentioned it that the Lewis diagram, you can make use of your dots or you can make use of your crosses to represent the valence electrons around the central atom, like how I showed you. Now, the most important part is let's talk about the covalent bond. Now, the covalent bond, it is a type of a bond that occurs between the 2 electrons, whereby the electrons are being between the 2 atoms, whereby the electrons are being shared, right? And then we have what you call a single bond. How do you see that we have a single bond? If you have atom A, and then atom A comes with its 1 electron, and atom B comes with its 1 electron. So these are 1 1, right? So this bond over here, it is called the single bond because of 1. You can represent it like this using a line. Okay, it's a single bond. But when you talk about the double bond, 1 electron pair is being shared between the 2 atoms. But when you talk about the double bond, atom A comes with 2 electrons. Atom B also comes with 2 electrons. If we want to represent it in terms of line, we're going to have A, 1, 2 to show that this is a double bond. Now we have 2 pairs of electrons that are being shared. Here we have only 1 pair, and then here we have 2 pairs. It's a double bond. Here it's a single bond. And a triple bond, atom A comes with 1, 2, 3 atoms. Atom B comes with 1, 2, 3 atoms. We have first pair, second pair, and the third pair. We can also present it like this: 1, 2, 3, B. So this is a triple bond. 3 pairs of electrons are being shared between 2 atoms. When 2 pairs of electrons are shared between 2 atoms, we are talking about a double bond. When 1 pair of electron is being shared between, we are talking about a single bond. By the way, this type of bonds, we call them the covalent bond. Why? Because the paired of the shared electrons, there are shared electrons between the 2 non-metals. Okay? Right. Now I want us to quickly do the examples of Lewis diagrams. Should be able to know how to draw the Lewis structures. So here's the question. Say to us, represent hydrogen chloride, which is HCl, using a Lewis diagram. So these are a few steps that I want you to follow when you draw your Lewis diagrams, okay? So step number one, this is what we're going to do. We're going to determine the valence electrons in the atom and represent these using dots and crosses. So firstly, let us start with how many atoms are involved in this compound. We have two, which is H and Cl. Now we have H this side and we have Cl this side. So we want the number of valence electrons for each atom. So hydrogen, if you forget, you go back to your periodic table, you can see that hydrogen, it is in group 1. So how many valence electrons do we have for hydrogen? Definitely it's going to be 1. So we have only 1 valence electron. Then we do the same for chlorine. So chlorine, it is in group 7. If you still do remember, it is in group 7. There is chlorine. Here's our chlorine. It is in group 7. So how many valence electrons for chlorine do we have? We have 7, right? So we have 1, 2, 3, 4, 5, 6, and 7, meaning it is surrounded by 7 number of valence electrons. That's the first step we need to do. Okay, you look at your atoms, you look at their group numbers, and you write their valence electrons. And in step number 2, which is the last step, it's not have to be, this thing's not complicated. Step number 2, you arrange the electrons so that the outermost energy level of each atom is full. Like I said, hydrogen, it won't obey an octet rule. Chlorine, it is the one that obeys an octet rule because it's supposed to be surrounded by 8 number of electrons. So now what you do is we can see that this hydrogen will share its electron with chlorine, and chlorine will also do the same, will share its 1 electron with hydrogen. And then now we have a molecule that looks like this. So this will be for hydrogen, this will be for chlorine, and then we write our Cl as it is and continue to write all of these electrons. 1, 2, 1, 2, 1, 2. Now, when you have a look at chlorine, chlorine must be surrounded with 8 number of electrons. Now, we can see that chlorine, it is surrounded by 8 number of electrons, which is 2, 4, 6, 8. It obeys an octet rule. And in hydrogen, it needs only 2. It doesn't have to be surrounded by 8 because it doesn't obey. That's the exception. Hydrogen doesn't obey an octet rule because its energy level, its outer energy level, it doesn't take a maximum of 8 electrons. So now this will be our final answer to the question. Simple as that. Now let's do another question where we want to determine the Lewis diagram for water. We're gonna follow the same steps. Okay, we're gonna follow the same steps. H2O. So H2O, this is how we normally write H2O. So what you do is you write your atoms that are involved. That's step number 1, right? Atoms that are involved, we have hydrogen and we have oxygen. How many hydrogen atoms do we have? We have 2. You can put your 2 over here, right? Or you can say H and another H. It's still fine. Step number 1, what do we do? Find the group for hydrogen. It is in group 1. How many valence electrons do we have? It's going to be 1 because it is in group 1. And then for oxygen, you also do the same. It is in group 6. Let's go confirm from the periodic table. Yes, it is in group 6, right? Oxygen, it is in group 6. And oxygen, it has how many number of valence electrons? 6, because it is in group 6, right? So we have 1, 2, 3, 4, 5, and 6, right? This is the oxygen. We have 6 number of valence electrons. And then step number 2, what now do we do? We obey an octet rule. Now, this is what I want you to understand. We have 2 atoms of hydrogen, meaning it's more or less like so, right? Let me now erase that 2. Now, how can we combine this? So this hydrogen, right? Uh, this hydrogen, okay, let me do this. I did there, so it can be nicer. This hydrogen will, then let me fix that one. I want to make it a little bit nicer. And we put it here. So this hydrogen will share its electron over there to oxygen, and this oxygen will also share its electron over there to hydrogen. Same applies to here. This will share its electron over there, and this will also share its electron over there. Then we're going to have something that looks like this. We have H, we have O, we have another H over here. So we have these 4 guys over here. 1, 2, 3, 4. And then we have this guy over here, and we also have that guy over there. And then hydrogen will bring its electron to be shared along with oxygen, and this hydrogen will bring its electron to be shared with the oxygen. And then if you count the number of electrons surrounding oxygen, we have 8 now, which obeys an octet rule. Then for hydrogen, we have only 2. For this one, you only have 2, and then this will be the final answer. Now let's do presentation for oxygen gas using Lewis diagram. How many oxygens are involved over here? There are only 2. So meaning it's something that looks like this. 2 oxygen atoms. Corp 6, we have 1, 2, 3, 4, 5, and 6. Right? So let's break it. We have 2, which is 1, 2, 3, 4, 5, and 6. Even this one, we're gonna have 1, 2, 3, 4, 5, and 6. Now, how do we combine these two guys? You must make sure that when you combine them, you obey an octet rule. Ne? Now, let's do it in trials so that I can show you something. Now, if I put this oxygen over here, and then I say 1, 2, 3, 4, 5, 6, and then I put another oxygen over here, I say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Or let me put it like this. 6. Now having a look at this, if I say this oxygen will share its electron with this, and this oxygen will share its electron with that, now our result will look like this. 1, 1, and then we're gonna have 1, 2, 1, 2, and then we have 1. Then let's do for this one. 1, 2, 1, 2, and 1. Now let's count the number of electrons surrounding this oxygen. They're supposed to be 8, right? We have 2, 4, 6, 7. You see? So this, it doesn't obey an octet rule. Why? Because it is surrounded by 7 number of electrons. So that means this is a trial, and then we see this, it doesn't work. Now what do we do? What we do is then we transfer this electron over here, right? It's gonna be like this. Then I erase this one. Then we also transfer this one over there. And then that side we have 2 again. Now let's see then. So meaning these 2 electrons and these 2 electrons are the ones that are going to be shared between these 2 oxygens, right? So let's work it out that side as well. So now we are sharing two electrons, no longer one. We share this, we share that, we share this for this guy and this one. Now let's count number of electrons surrounding this oxygen. We have 2, 4, 6, 8. Now this oxygen has obeyed an octet rule. Same applies to this one. Will also be 2, 4, 6, 8. This one will also obey an octet rule. And therefore now this is correct. This is how we write our final answer. So by the way, if you have a look at this, we can see that we have only one pair of electron being shared, one pair of electron being shared. So this one pair is a single bond. And then again, we have two bonds over here, right? Here we have only one pair of electron being shared, which is single bond. Here we have two bonds, one with single bond. And then here we have two electrons that are being shared between the atoms. Therefore, we have the double bond. So meaning it can also look like this. One, this, and that. Okay, right. So let's do this last question where we have the hydrogen cyanide. We want to determine the Lewis diagram for it. Again, firstly, separate your atoms. We have HCN. Okay, we have HCN over here. Now, what I want you to understand is you should be able to break this into their atoms, right? So, how many atoms do we have? We have HCN, we have hydrogen, carbon, and nitrogen. So we have hydrogen, carbon, and then nitrogen. Step one, valence electrons for each. So for hydrogen, we know it's going to be only one because it is in group one. And then for carbon, we know that carbon it is in group 4, so we're going to have 4. 1, 2, 3, and 4. And then nitrogen, let's go back to the periodic table. Nitrogen it is in group 5, so that means we know that we're going to have 5. 1, 2, 3, 4, and 5. Right. And the question is, how do we combine these guys over here? So carbon, it is the middle atom. Okay. Carbon is the middle atom. So how do we combine these guys together? Let's do trial and see if it will work. Now, carbon, we have 1, 2, it will share with hydrogen on this side. Then we're going to have something that looks like this. And then we have this one over here. And then we can see nitrogen can also share 1 electron. Let's put it there. Now let's see if carbon obeys an octet rule. We have 2, 4, 6. We have 6 carbon atoms. So carbon doesn't obey an octet rule. So this is wrong. Let's check nitrogen obeys an octet rule. We have 2, 4, 6. Also nitrogen has 6. It is surrounded by 6 electrons. So it doesn't obey an octet rule. Now, what do we do then? Remember, hydrogen and carbon cannot have a double bond. Why? Because we know that hydrogen needs only one. So it is satisfied with one. So there is nothing wrong with what is happening on this side. But we need to manipulate this side. So now what we're going to do is we're going to move one electron over here, right? And we will move this one electron over here. Carbon and nitrogen can do double bonds. Let's see if that would work. So I'm gonna erase this one over here. I'm gonna erase this one over there. Put my cross here, put my dot there. Then let's see if this one will work. Let's see if this one will work. Now I have two atom electrons. Then also that side I have 2 electrons. And then let's see, 1, 2, this. Now let's count the number of electrons surrounding the carbon. So we surround this, it's gonna be 2, 4, 6, 7. They are now 7. Instead of 6, they are now 7. You see, they are increasing. But still, we haven't obeyed an octet rule. Even for nitrogen, we can see that we have 2, 4, 6, 7. Yes, it is also increasing. We have 7. We need 8. Still, it hasn't obeyed an octet rule. Let's further manipulate this. We can see that we have electron that is standing alone. We can bring it this side. Even this electron, we can also bring it this side. See, now we have 3 electrons. Let's erase that now. Then we can do it like this. For carbon, 1, 2, 3. We brought all of those electrons this side. For nitrogen, we bring those 3 electrons also this side. Then let's see if this now will work. So now we have 1, 2, 3, and then for nitrogen, we also have 3. Now we have 3 pairs of electrons that are being shared between carbon and nitrogen. Now let's count number of electrons surrounding the carbon. We have 3, 6, 7, 8. Now we have 8 electrons surrounding the carbon atom. Let's look for nitrogen. There's supposed to be 8 as well. 3, 6, 8. Now we have 8 electrons that are surrounding the nitrogen. Now this is correct. This is how we write the Lewis diagram for hydrogen cyanide. We can also write it like this. 1, 2, 3, it's a triple bond. And then we have the lone pairs. So this is how we can also present it. Okay.